Hello everyone, this is Singh and today I'm back with another system design video where we'll be deep diving into another architecture of Uber, which is Uber's real-time push platform. So how the notifications are delivered, there are different kind of notifications which has to be delivered to the users in real time, how these notifications are pushed to the user devices or the mobile devices. We will be deep diving into that. Our discussion is based on this particular blog which you can read, and I will share the link with you in the video description. So let's get started. Okay, so again, if you haven't subscribed to the channel yet, so keep subscribed, and if you haven't already, then do subscribe it. Okay, you will get to know a lot of design details, lot of system architectures, and we will be deep diving into a lot more in the coming days. So starting off, how do you do it? Okay, so the first approach is that the requirement, basically, right? Before going to approach altogether, let's discuss the requirement. So the requirement is very simple. You want to deliver the notification, so you have your mobile device, and this is your, let's say, Uber server. Okay, and these are a lot of multiple mobile devices. You have to deliver some kind of notification. Let's say your drive, your car has arrived, or let's say in case of Uber Eats, your food is in preparing state. Okay, so there are different kind of notifications which needs to be delivered to the users, and we have to make sure that they are delivered reliably in a fast fashion. So the first approach is that your mobile application here, what it do, it connects with the app. So this is our app, it connects with the app. Okay, this is your app, and it connects with the Uber server, and then it keeps on checking for the updates. Now let's say I placed an food order. Now if I placed an food order, I will keep on checking, let's say every 5 seconds, what is the status. So we have a simple status API. What is the status? So basically, let's say in first call, I get the status as, yeah, the order is placed. In second status, it's in, let's say, processing. And in consecutive calls, it still gets processing. And let's say after 15 minutes or so, you receive on the way. So this is one of the way that you keep on polling for the updates. I have also made another video where we discuss these things, like what is polling, what is long polling, what is short polling, and then WebSockets and all those kind of things, right? So the polling approach is very simple. The application keeps on making the HTTP calls at a regular intervals. In short polling, it do not hold the connection. In case of long polling, it holds the connection for certain time if the response is not arrived. But in all the scenarios of polling, like however you want to do it, short polling or long polling, it is highly probable, it is highly possible that the response you get is same. Okay, it's processing for 15 minutes. So the defining of that interval, okay, so the one of the requirement is that real time. We want to deliver the notifications real time. How will you able to do that? Now if you want to do it real time, you want to ensure that 5 second interval, again it's a kind of large so that it can fall into the real-time behavior. But let's say even if we have 5 seconds, there is highly possibility that you do not get the updated status every time, or like the status is same every time. So due to this, it leads to increased server utilization, because you are hitting the server. So in that case, your resources are being utilized on the server, right? So whether you get a response or not, you are serving that request from the server, and this leads to increased server utilization. So this is one of the bottleneck, you can say, at a large scale in case of polling. Great. So large server utilization, many times the polling calls get empty, and so on. We already discussed that. Another thing is, any bug in polling logic can bring entire infra down. Okay, when I said this, so we mentioned that you have a mobile app. Okay, you have a mobile app, and then you have your server. This is your server. Now let's say instead of 5 seconds, someone messed up the configurations and made it 5 milliseconds. Okay, now This simple change can increase the load at the system at a very large scale. Like the load which you think, right, from 5 seconds to 5 seconds, it will increase exponentially, and it can bring the entire infra down. So these are the issues which can occur with the polling. Another thing is, you are making that continuous call every 5 seconds, or let's say 2 seconds, so that interval is defined. You don't know when will you will get the response. So these are the issues which you can have. Faster battery drain, because your app is continuously polling for the response or the status of that particular order which you placed. App slowness, because this is the single call we discussed. Similarly, there are multiple invocations or multiple paths where the polling is being done. Network layer congestion, again, this is again related to, since you are increasing the traffic, it is increasing the network calls, so there is a chances of congestion which can occur in the network. So in a nutshell, this is not an ideal approach. Okay, this is not ideal approach for anything at a large scale, but it becomes very hard for, again, 2G or 3G networks, which can happen in the remote areas. So if this is the network area, this is the remote area, and you have 2G or 3G network, and then you are making the call and the network is very slow and you are not getting a response, your app becomes slow. So in short, there are a lot of issues with the polling. We are moving to the solution. Another is the cold startup of app, which means this is one of the call, right? So whenever you open an app, so let's say whenever you open an app, there are multiple screens here. Each screen polls for something, okay, and to ensure that everything is updated every time, they keep on polling. So this increase the cold startup time. So cold startup basically means whenever you open the app, there are a lot of loading that comes up. So instead, the solution should be that you show whatever you have available, you cache the data in the mobile device, and then you later fetch it and then update it. So that is one of the solutions. We already discussed that kind of solution in the Instagram newsfeed system, where you show whatever you have in the app and then you further update it as you receive the response, so that the user is not blocked and the experience is maintained, and due to cold startup of issue, experience is not hampered of the user. Great, we have discussed what the issues with the polling. We discussed polling is one of the approach, and then there are multiple issues with the polling. So what is the solution? Solution is RAMEN. RAMEN is real-time asynchronous messaging network. This is the name the Uber has given. We will discuss what RAMEN means. I'm not sure of this pronunciation of the word, but let's say it's RAMEN, okay, real-time asynchronous messaging network, and we will try to grasp the idea of what is being done here. It is much similar to, if you have seen my WhatsApp video. In that video, we maintain a persistent connection with the user devices, and then we keep on delivering the messages, whatever you receive from users, and you know that what is the intended recipient, and based on that intended recipient, you figure out which server it is connected to, and depending on that, that message is delivered. So your RAMEN here is, in short, that front-end service or chat daemons which hold or maintains the connections with the user devices, and then delivers the notifications whenever they are received. So instead of polling, you are delivering the notification. So instead of instead of poll, you are doing push. So this is your poll, user device to server. Instead of doing this, there are a lot of issues which we discussed here. We are doing this, which has lesser issues. Cool. Now to the like a very high level architecture of RAMEN. It involves three services specifically. First one is the firewall service. Firewall service figures out when to push. Okay. API gateway figures out what to push. Okay. RAMEN server figures out how to push. So we have three questions: when, what, how. Okay, and these are solved by the different components in our architecture. Let's get into the details of each of these components, but before that, there are few considerations before moving to any architecture. Let's say this is your arc 1, which is based on polling. and there is another architecture arc2 which is based on push based architecture. You are moving from this architecture to this architecture. So what are the different things you should consider, okay, so that your migration is easy? Okay, this because this is already deployed and it is serving the customers, and then you want to migrate to this because this is better and more efficient approach. And the migration process should be smooth. From user perspective, they should not know that whether you are doing push or pull. They don't care actually. They just want the notifications to be received, and the experience should not be impacted. Great. So what are the considerations? Easy migration from existing polling in production. Great. We want a easy migration approach, easy code development. Whatever new logic you are writing, it should be easy to develop. And if you are modifying any polling logic, it should be done reliably so that the existing traffic is not impacted. So the idea here is you have your user pool which is already being served by the polling logic. This should not be impacted. Okay, so all the considerations which are discussing here, they're depending on that only, that the existing user pool or whatever new users are being onboarded, and if their polling approach is used there, it should not be impacted, and the migration should be smooth without any downtime. Reliability. Message should be retried for delivery failures. So this is one of the consideration which we have to make in the new architecture, that if there are any, and this specifically uh, holds true for the messages which are of high priority. Okay, let's say of some of thing of payment notification. So those notifications has to be delivered, and if there are any failures in delivering those notifications, then you should have some kind of retry mechanism so that you can do that. Wire efficiency. Wire basically means the network. So server device, we have drawn it so many times, but this is the wire actually. Wire basically means the network through which the payload travels. Minimize amount of data transfer between server and app. Why? Because we wanted to solve this problem: faster battery and app slowest network level congestion. So if on a slow network the payload size is less, it is easy to deliver that payload as compared to a larger payload. So we want to do that as well. Great. Now how we are doing this? So this particular architecture, let's clean a little bit. So this particular architecture, okay, this particular architecture, what we are trying to do here, we discussed that firewall service figures out when to push, then API gateway figures out what to push, and RAMEN service is responsible for delivering these notifications, basically pushing those notifications out to the users. So deciding to generate a message. Now how will you know if I have to send a message or not? So there are a lot of events which keeps on happening in the Uber. Let lot of microservices, right? This is M1, this is M2, this is M3. These services keep on publishing multiple events. Let's say this particular customer has placed an order. Okay, so these events, let's say these are SNS topics, or this is some Kafka topic, and there are Kafka consumers here in the firewall service which consume these messages, different messages which arise. And depending on, so let's say this is your firewall service. Okay, this is your firewall service, and let's change our color to black. Okay, so you receive multiple events, E1, E2, E3, and you have your consumer handlers written. This is CH1, this is CH3, this is CH4. This handler consumes this particular event, then it checks particular some configurations, what needs to be done for this particular event, and depending on that it identifies when to push. Okay, it figures out when to push. So basically time or priority and all those things, it tries, the responsibility of firewall is doing this. So there are different handlers which are present, which consumes different kind of events that happen across the Uber system, and then make a decision when to push a notification. There might be a chances that you have to drop this event altogether. Okay, you don't have to push any notifications for this particular event. Great. So figure out when to generate a payload for a user. consumes different kind of events, determines if message push based on example user requesting a device. Right, great, we discussed this. Firewall also fetches device context. So one more thing which is useful here is the Uber is used in multiple marketplaces, lot of marketplaces. It is used in India as well. Let's say there are different states and a user has selected a particular language as of preference. Okay, let's say Hindi is one of the language, Marathi is another language, English is another language. So there are different device contexts which are being set. Okay, there are different device contexts which are being set, and depending on these context, what you are doing is what you are doing is what you are doing depending on this context, what you are doing, you figure out what's the localized message or localized payload that has to be delivered to the user, so that that can be sent to the user based on geography or like any other preferences. Geography is one of the thing, but let's say in the India geography and in Rajasthan, Hindi is one of the preferred language, or English is one of the preferred language, right? So depending on the user selection, we want to deliver the notifications. So device context help us with that. Now, to message payload generation, firewall determines who to push and when to push. API gateway determines what to push. Okay, what to push, this is when to push, and then also who to push. Depending on the events, it also figures out like to which user this message has to be delivered. So this is figured, and now we are going to this component, what to push. Let's discuss the API gateway part. So API gateway determines what to push. Now API gateway can be of two types. It supports push APIs, it supports pull endpoints. So these push endpoints are basically enabled for only firewall, and it also has a middleware which can intercept the response of pull API. Okay, so this is your API gateway. This is your mobile device, and let's say you have your pull API. Okay, get me some information, get user status. This is a simple API, and I'm not sure what it is doing, but let's assume that we have a API get user status. Okay, and as soon as it receives this API gateway, we have a very thin layer in between. A middleware is just a software which intercept this response. Okay, assume it as a interceptors in your Spring Boot framework. Okay, so we you intercept this request, and what you do, you intercept the response of the and forward to push based delivery mechanism. So let's say you want to take some actions on top of that. So whatever response you receive, you intercept that response and then you forward that to push based delivery mechanism. Pull are basically endpoints called from F or HTTP operations. There are different APIs which are being exposed, and the endpoints are being invoked from the app to receive the response, much similar to get user status. Great. Why we are doing this in the API gateway? So actually, API gateway is already in place. So we want to get some other benefits. Why reinvent the wheel? Okay, why reinvent the wheel if something is already implemented? So let's reuse. So payload can be easily switched from pull APIs to push APIs. We want to support both kind of endpoints. Okay, so we have your notification delivery as one of our use case. There are other use cases as well, right? API gateway serves all those use cases. So in future, if you want to switch among the push and pull, it can be easily done. There are other features which are already developed, such as red limiting, schema validations, routing to different microservices. So these things are already implemented or launched at a API gateway level. So why not leverage it? Great. So that's why we are using the API gateway to what we are doing, what to push, figure out what to push. So once the payload is generated, it is delivered to mobile devices with the help of push based delivery system. This is your RAMEN, push based delivery system. Now there are different metadata for push messages as well. What are the metadata? There are three metadata basically. One is priority. What is the priority of these notifications? I mentioned that we might have notifications for payments related. These are of high priority, right? So basically we have simply categorized into high, medium and low. So the high priority notifications should be delivered quickly as compared to some low priority notifications, or like let's say deduplication logic. Okay, you want to have the you do not want to send that same payment notifications multiple times. So these are the things which you have to ensure. Priority is one thing. Another thing is time to live. Time to live is basically till what time you store that message or retry that, so that it can be retried if it is not delivered and all those things. So basically, what is the time frame in which you keep that message in the database? Few seconds to 30 minutes message delivery persists to message as per TTL, and retries or failures in this time window. So let's say this particular message is of high priority and the first delivery of this notification failed, then you retry this message uh, depending on that configurations. This can vary from few seconds to 30 minutes, but yeah, it can depend from use case to use case. Deduplication is basically, as I mentioned there, if you are retrying the notifications, there is highly possibility that the idea is that you have to ensure that you are not delivering the duplicate notifications. So one way is that you have a deduplication ID or some sort of ID from which you can track easily that this message was already sent, and then I hope to don't send it again. Moving to the message delivery part, that's where our RAMEN architecture comes in picture. So the idea is, all the user devices we already discussed at the start of the video, or it is much similar to the WhatsApp architecture, where we discussed that the mobile devices or the user devices are maintaining a persistent connection with the backend server, and then server push the notification, whatever the notification is. So maintain active connections with the mobile devices, forward the notifications when received. It's pretty simple what to do. So there is persistent connection with RAMEN server, and whenever a notification is received, it is being delivered to the client. Great. So RAMEN delivery protocol is based on SSE, server sent event. Server sent is event is basically unidirectional connections, which helps in delivering the response, or is delivering some kind of payload from the server to the user device. How it works? It is built on top of TCP, and these are the basically reasons why the SSE was selected as a delivery protocol in this case. Later on, Uber moved to gRPC, which Uber has a different blog altogether. There are some limitations with SSE as well, but in this blog, or like this video itself, we will be discussing SSE and how the architecture is designed on top of SSE. Now, one thing which we need with SSE is we need acknowledgement from device. We mentioned that, let's say a message is priority notification. Okay, we want to ensure that this notification is delivered. And how can you do that? You need acknowledgement for that notification. Okay, you need some response from the device that this notification was delivered. So what you want, since SSE is unidirectional, sending acknowledgement from the server requires additional implementation. Let's take this example. Okay, let's take the example. Connection is established with sequence 0. This sequence 0, sequence 1 are basically this incremental numbers which are maintained for these messages, and they are helpful to figure out, like, whenever the message, or like whenever the connection is dropped, they are helpful in figure out till what point the messages were delivered, so that they can be retried from the next point. Okay, so let's say the message with sequence 1 was delivered, message with sequence 2 was delivered, message with sequence 3 failed, and then some, let's say some timeout happened or some issue happened. Now, since this is a TCP connection, since this is a TCP connection, it is being retried. Okay, whenever it is being retried, it will be retried with a sequence 2. Now the server will know, the RAMEN server will know that the sequence 3 was not delivered, because the device is requesting for sequence 2. So in this case, the message with sequence 3 is sent again. We didn't discuss the connection setup part, how the connection works basically. So how the connection works is, you call this particular API, and this SSE is established, and this is the header which is being text event stream. This is how a normal simple, you can say, HTTP connection is converted into SSE. How SSE works, this we discussed. Great. Another thing which we need in our system is, how will you figure out if the connection is alive or not? Okay, we want a reliable mechanism again on that front, that basically a heartbeat mechanism, that how your to figure out if the connection is live or not, so that you keep on sending those notifications. So for that, what you do is server sends a heartbeat message every 4 seconds to the user device. Okay, so every 4 seconds, 0 second, this is 4 seconds, so every 4 seconds it sends a heartbeat message to the user device, are you connected to me? Okay, and at a client level, so this implementation is done at both levels, at the server level and as the client level. If client do not see a heartbeat message in 7 seconds, it assumes a connection is broken and then reestablishes the connection in the similar fashion. It sends the call, it makes this HTTP call with the particular sequence number. Okay, and then this event header is received with text event stream, which means SSC connection is being established. Now, okay, we are clear with the heartbeat mechanism to ensure that how we make sure that your connection is live or not. Now, the another thing which is important here is how will you remove the messages from server. Okay, we mentioned that, let's say sequence 1 was delivered, sequence 2 was delivered, sequence 3 was not delivered. Now, how will you figure out that when you want to delete these messages, because we mentioned that we need acknowledgement mechanism. Okay, we need acknowledgement mechanism so that whenever you receive acknowledgement that these messages are delivered, then I can safely remove them. Now, what is the mechanism which is being used? So whenever a client connects with the server, all the messages are flushed out. Okay, so in this case what we did, we re-established the connection with sequence 2. So in this scenario, we can know the older messages, sequence 1 or sequence 0, will be removed from the server. Great. Now, let's say a connection is very reliable. Okay, the connection is very reliable. Now, in those scenarios, a connection might keep for several minutes, but it will accumulate a lot of messages on server. Now, to flush these messages, okay, to flush these messages, app calls this particular API every 30 seconds. RAMEN acknowledgement sequences we mentioned that we need acknowledgement mechanism, and this is our acknowledgement mechanism. Every 30 seconds you call this API, irrespective of heartbeats or whatever mechanism you have, you call this API every 30 seconds, which means let's say this sequence is 30, so remove all the messages from 0 to 29. This is what you have to do when you say that you are deleting or flushing out all the older messages, because once the messages are delivered successfully to the user device, there is no point of keeping them on the server and increasing our storage space. Great. Now, all the things which we discussed, all the things we have discussed till now, what is the architecture implementation, this helped us till this QPS. You have a QPS of 30K, which is great. 70K requests per second, and then these are the number of connections, these are number of the user devices which are concurrently connected with the RAMEN server. And this existing implementation is based on the Node.js library. There are few limitations which Uber encountered with this particular architecture, and then they later on evolved it to scale it further. Okay, so what are the limitations? One of the limitations was using this particular library for sharding mechanisms. So we have a multiple nodes, right? In architecture, we mentioned that these are the user devices. These user devices are not connected to a single server, right? You have a multiple servers. Okay, you have multiple servers which establish these connections and then deliver the notifications to the user devices. Now, this ring pop library, which is being used for sharding purpose, doesn't scale as the number of node in ring increases. Why? One of the reason is gossip protocol use. It uses the gossip protocol, and as the number of nodes increase, gossip protocol works on the concept of sending a message to every node, or like passing on those messages to every node to deliver the particular information. So this is how this ring pop library works. So time of convergence increases, number of node in the ring increase, because they have to deliver this node informs this node about, like, let's say this particular node is not available. Okay, this node informs this node that this particular node is not available. So this is how the broadcasting of messages happen in case of gossip protocol. So this was one of the limitation. Another limitation was single threaded Node.js workers. I haven't specifically worked with Node.js, like how the architecture works, but there were some limitations which are associated due to the single-threaded nature of Node.js, which led to elevated levels of event loop. Again, as I mentioned, I haven't worked personally too much into the details of how Node.js works or how it works at scale, but I'm assuming here that since it's a single threaded, and if there are a lot of notifications which are being delivered, and let's say for a single user you have to the single thread is basically responsible to deliver the all notifications, right? So let's say this is work 1, this is work 2, this is work 3. So once work 1 is done, okay, or it is on hold, it is trying to do the work 3, work 2, or work 3, depending on the availability of the thread. You have a single process and you have multiple threads. As and when one thread work is completed, it will pick up the another thread work of another thread. So basically you have a single process which does all the work. Now there is enhancement to this architecture, which is this, okay, and it is divided into front end and back end component. Your front end basically works as a proxy service, okay. So to this front end you have your multiple systems which it talks, right? One is your RAMEN, not RAMEN, one is your firewall, okay. So there are multiple APIs which talks to it, and then you have your this stream gate. Fe is basically your front end component, and this is your back end component, okay. So this is how the architecture is divided. There we will discuss the multiple components of it, how it works, and then we will end this video. Now in the enhanced architecture, there are a lot of new components which are introduced. One is this 𝐴𝐽keeper. You might have already heard about it. You basically use it for the coordination, okay. Earlier we were using ring pop, okay. We were using ring pop. The idea is that you have multiple nodes in the server, right, where the user devices are making the connections. So you are using that library to make sure that whenever a new node comes up or comes down, you manage those user device connections reliably, okay. So you replaced that library with two components. One is 𝐴𝐽keeper, another one is Helix. This is cluster management software, Apache software. 𝐴𝐽keeper is your coordination library which we are using. So these are the two components which we are using. Helix is one component which you might have heard, which you might not have heard about it. This is the first time for me as well to get introduced to the Helix. 𝐴𝐽keeper, or definitely I have explored it with multiple architectures, but yeah. So these are the new things which are introduced here. First thing is Helix. Where is Helix? This is the Helix. So this is a cluster management frameworks, and it works on top of 𝐴𝐽keeper, okay. And you, in this cluster management framework, you can define your custom topologies and rebalancing algorithms. Whenever I say these algorithms and topologies, like the mechanisms in which you want to ensure these different nodes which you are maintaining, okay, different nodes which you have, different hosts which you have in your architecture, in your cluster. So you can define your own algorithms how you want to rebalance them. Basic one of the thing of rebalancing, let's say, is uh, let's say you have three nodes, okay, three hosts, h3, h2, h1. Great. Now this, if this h2 goes down, okay, if this h2 goes down, you want to shift some of the traffic of it to h1, and then some of the traffic to h3. This is a simple example of rebalancing, okay. So your Helix is your cluster management framework in which you can define your custom uh, topologies and rebalancing algorithm, and it uses 𝐴𝐽keeper for monitoring of connected workers. Whatever workers or hosts or nodes which you have, 𝐴𝐽keeper is used as a coordination system. Distributed synchronization and configuration management can detect failures of connected nodes quickly. This is what we are using. Netty is used as a backend server, so it is much similar to your Tomcat. We use Netty generally in case of high traffic to develop high traffic concurrent applications. So this is your just a server which keeps on accepting the connections and then take action on top of them. Another architecture which we have, storage is another component. Now these are the two components, like what what we have in the architecture. One is the front end component and another one is the stream gate, which is the backend. Again, we have discussed front end separately here as well, but the stream gate FE specifically here, what it does is it acts as a, so there are two jobs it does. First one is it acts as a spectator. Spectator basically means it observes, okay, and whatever changes which happen in the node architecture or whatever host we are maintaining from the zookeeper. So zookeeper, let's say, publishes any updates and it observes those updates. It also acts as a reverse proxy. So when I say reverse proxy, it consumes or like receive the updates or not receive the invocations from multiple clients such as firewall or mobile app, and then it redirects to the appropriate streamgate worker. So streamgate worker doesn't has to know the context from where the request is arriving. Okay, I don't have to worry about it is arriving from firewall or mobile app. It is abstracted out by the streamgate FE or front end component, and then it is being sent to the streamgate. Streamgate has this RAMEN protocol on RAMEN server. When I say RAMEN protocol is SSC plus some of our additional implementation of acknowledgements and all those things. Okay, this is what we mean by RAMEN protocol. So RAMEN protocol on NetE servers handle connections, messages, and storage. Okay. Great, you are maintaining different connections. You have a lot of connections with the user devices. You are maintaining those messages and it also store those messages from the time being or whatever TTL we have configured. It also implement the Helix participant and establish connection with the zookeeper, and it maintains the heartbeat. So these are the few things we already discussed, that we need acknowledgement, we need a heartbeat, and then we also need a Helix participant to establish connection with the zookeeper. Controller is basically your mechanism, or you can say a software which is part of the Helix, which is responsible for control plane operations. Okay, so it runs the Helix controller processes responsible for topology management. For any streamgate node addition or removal, it detects the change and reallocates the sharding partitions as per the algorithm or as per the custom algorithm we have defined. On the storage front, we are using two stores. One is Redis as a cache and Cassandra as a source of truth, which ensures that data is replicated across the regions. You have application which is deployed on multiple regions, R1, R2. The data is replicated across the regions using Cassandra, or Cassandra is used as source of truth and the durable store with multi-region replication in place, and Redis is just used as a capacity cache on top of it. Okay, and one reason for using Redis is it helps in avoiding thundering herd problems on hand deployments, failure events in sharded system. Let's quickly explain this statement. Okay, so what do we mean by thundering herd? Thundering herd is basically, let's say some issue happened with particular request R1. Okay, and then you have R2, R3. Okay, these are the multiple requests which are coming to our backend server. Okay, let's say this is your RAMEN server. Now let's say this particular request failed. You want to ensure that if some failures happen, there is no bombarding of the request that can come to this RAMEN server. So to ensure that the requests are resolved via caching mechanism, okay, the requests are resolved via caching mechanism, and you are not hitting your Cassandra or your what do you say, durable store which you have, you are using Redis as a capacity cache on top of your data store. I'm hoping I didn't made it more confusing, but the idea is simple, that you are using Redis as a cache so that you reduce the duplicate traffic on your storage. Great. And just on the metrics part, the architecture, the improved architecture is supporting 250 QPS, 250 transactions per second, and 5.5 million concurrent connections, which means you are currently connected to 1.5 million mobile devices. So this is all about today's discussions around Uber's real-time push platform. Again, to summarize what we discussed that there are some issues with the polling. To resolve the issues with the polling, we are moving to the push based architecture. One of the architecture which we discussed today is the SSE, which is based on, which means server sent event. You are sending the notifications instead of polling for the notifications. You are pushing the notification from server to the app. And as I mentioned earlier, there is an improved architecture on top of this, which is based on gRPC instead of SSE, which is bi-directional protocol to deliver the notifications, which we might or might not discuss in the upcoming videos, but I will definitely read that blog. And in that video we will also discuss limitations in this architecture. So, and if you haven't subscribed yet with the channel MsDeep Singh, keep subscribed. And also my book is coming, which is System Design on AWS. It's already available on O'Reilly platform. Do give it a read. It's a great book to deep diving into multiple architectures, how you design systems using AWS components at scale as well as at very low scale. So we will meet again. Till then, stay safe. Tata. Bye bye.